So we'll finish up our treatment of wave optics by taking a look at diffraction gratings. Now this is another one of those drawings that I have to do where all I can say is not even remotely to scale. Remotely to scale. So what a diffraction grating is a series of very finely spaced slits. So you have a whole bunch of slits spaced very close together. So this makes D incredibly small. And out here is my screen. So if I have light coming in through here, what will happen is each one of these slits will have wavelets propagate out. And you can show that they interfere out in the same way that would happen with Young's experiment, double slit diffraction. So the upshot is that you'll have some central maximum. Pardon me, let me draw this more carefully here. Oops, it'll do the intensity this way. So this is my we'll do the intensity this way. This is my central maximum. I'm trying to draw it very skinny. And then off over here somewhere might be my first order maximum. And then up over here somewhere would be the second order, etc. And then repeat down here. So we would have a first order. Then maybe down here would be the second order. And I'm intentionally not making the distances the same, although they should be the same vertically here. So let me fix that up. There. Yeah, okay, we can make this look a little less bad. Okay, so yeah, up over here somewhere would be our second order maximum and so forth. And I want this distance to be bigger than that, so let's move it up just a little bit more. Yeah, something like that. All right, great. So the idea is exactly the same as Young's experiment. The difference is that in Young's experiment, for a typical lab setup, all the angles are really small. With diffraction gratings, by design, the angles, because this distance between lines in the grating is ridiculously small, we can't use the small angle approximation anymore. And this is a feature, not a bug, because you want to get a big angular separation so that you can very precisely measure the wavelength of the light that you're detecting. So we can't make sine theta approximately theta, and we can't make tan theta approximately theta. So if, say, this distance here is y1, the distance of the first order, we just have to say d sine theta for the mth order will be equal to m lambda. We can't turn the sine into just a theta like we did before, and we have to say that ym is equal to L tangent of theta m. So you'll have to solve this, get an arc sine, and then stick it into here if that's what you need. In both cases, m is the order of the spectrum. It's not a mass or anything like that. will be equal to 0, 1, 2, 3, and so forth. 0 for the central maximum, then 1, 2, and 3, and whatnot. So you'll notice here, though, that I drew the lines as being very narrow, unlike Young's experiment, where you just kind of smoothly ran from a peak down to a dark spot. What you find in a typical the diffraction grating pattern is that you have very narrow spots of constructive interference, and all the rest of it's darkened out. Now, to prove this in general involves a lot more math than I want this treatment to have. But what we can argue in a more advanced treatment is you can say that the maximum intensity of a peak of the peaks of the spectral lines that we see, it goes as n squared times the intensity you would have if you just had one slit. And n is the number of illuminated slits. So the thing is that the amount of light that is striking the screen is proportional to n, just the number of slits. If I have n slits, I let in n times more light than if I had just one slit. But it turns out that the intensity of each of these peaks goes as the square of the number of slits. Well, you can't get something for nothing. And so in order for these peaks to be so incredibly bright, it means that the minima in between have to be much, much wider. So in these kind of interference patterns, you see a single bright line, then nothing, and then another line, and so forth. The big application for this is spectroscopy. So what I'm showing you here is a diffraction grating pattern for a light source where the gas inside is hydrogen gas. The light source is on the left. It's the super bright thing blowing out the image. Now, if you look over to the right, you can make out 3 lines. Maybe if your eyes are really good, you can pick out a 4th. But you can see definitely there's a red line, a blue line, and a violet line over towards the right side of the screen. These are all the first order spectral, the first order diffraction peaks for light of those very specific wavelengths. It turns out that atomic hydrogen in the visible only makes light in a handful of wavelengths. And each one of those will diffract through a different angle because the wavelength is different. By doing this, we can measure the angle and then go backward, figure out what the wavelength of the light is. We can also use this to figure out, and we'll see this much later on. Say you look at this one, this is the same thing, but for helium. And you can see that there's a different mix of colors. Again, a little hard to see the light from the light sources blowing out the image somewhat, but you can see that there's a big prominent orange line that you didn't see in hydrogen, and there's a greenish color that you didn't see in hydrogen, and so forth. It turns out that these colors, what colors we see, have to do very much with the electron cloud structure of the underlying atoms and molecules. And by doing this, but by looking at these, we can identify every isotope of every atom and every isomer of every molecule. In the next round of videos, we'll be starting up ray optics. See you over there.